Are you able to see my slides?
Yes, sir.
Okay. So this is our third NPTEL live session of Advanced Foundation Engineering course. In the last two sessions, we discussed about uh, how to determine the bearing capacity of shallow foundations for different scenarios, like if the base was tilted, if the base is on the top of a slope, if the foundation is founded upon layered soil, all those. In today's session, I'm going to solve some problems related to shallow foundation settlement and plate load test and all those things. Okay, so let's get started. Let me introduce myself once again. My name is sinjandebnath. I am a PhD student in the Department of Civil Engineering at IIT Kharagpur. So let's go to the first question. So, what is the first question? A plate load test, a plate load test done on medium dense sand using a square plate of size 305 millimeter gives a subgrade modulus of 30 meganewton per meter cube. Determine the subgrade modulus value for a footing with dimension 2 meter by 4 meter. Note that depth of the foundation and depth of the plate are same. So before starting this problem, I want to discuss some points with you, like how to determine the subgrade modulus for the footing. So generally, what Tarzagi did is that Tarzagi developed this the some formulas for plate load test. Actually, so plate load test, we do plate load test to find out the bearing capacity and the subgrade modulus for the soil. So what he did is that he did the tests with a square plate. Using a square plate, he did all the tests using a square plate of having size 305 millimeter. He did all the tests using 305 millimeter and developed some empirical equations to incorporate the effects of larger plates. Suppose you doing a plate load test using a bigger plate. Suppose like using 75 centimeter plate, 70 centimeter plate, 75 centimeter by 75 centimeter. So you need to incorporate the size effect. And suppose you are doing a test using a 305 millimeter square plate, and you want to find out the subgrade modulus for the footing. Like in this question here, it is 2 meter by 4 meter. So a plate basically is a small model of a big foundation, right? Shallow foundation. So we need to incorporate the effect. So what Tarzaki did is that he did all the tests using a square plate of 305 millimeter, the size of the square, okay, the side. So in order to incorporate the size effect, what he did is that this K value, okay, this K value is the subgrade modulus that you get using a larger square plate. Remember square plate. Suppose B dash by L dash. Okay, B dash by B dash. It is a larger square plate. Suppose your footing. What is your footing over here? The breadth of the footing. The breadth of the footing over here. B dash equal to 2 meter. L dash equal to 4 meter. Okay. So this K will be based upon B dash by B dash. That means 2 meter by 2 meter. So it will be equal to K1 B plus B1 by 2B. Okay. So what is K1? This K1. This K1 is the subgrade modulus that you get from using a square plate of 305 millimeter. Okay. This is the K that you get using a square plate of 305 millimeter. That is K1. Now, now, what is B1? B1 is 305 millimeter, corresponding to K1. Okay, see, K1 is the subgrade modulus for 305 millimeter plates, and B1 is equal to 305 millimeter. Okay, so what is B? B is B dash actually. That means we are incorporating. Suppose we find out the subgrade modulus using 305 millimeter square plates. We are extrapolating that value to 2 meter by 2 meter, not 2 meter by 4 meter. I will come to that how to incorporate the shape effect. See, 2 meter by 4 meter footing is a rectangular footing. After size effect, this one is we need to find out the subgrade modulus for a square plate. That is 2 meter by 2 meter. B dash into B dash. After finding out that, we will incorporate the shape. You will find it out when I will solve this problem. So first, let us solve this problem. So first, I will come to size effect. So let me write down the formula once again. K is equal to K1 B plus B1 by 2B square. This is for the medium dense sand actually. Okay, see, this question here it is mentioned that this is a medium dense sand. This particular equation is for the dense sand, for the any sand actually, for sand. Okay, so what we are doing is that, what is, first of all, let us see what is given in the question. So in the question, a plate load test done on medium dense sand using a square plate of 305 millimeter. So the plate load test was done using a square plate of 305 millimeter. So B1 is 305 millimeter. That is the test plate. Now, using the test plate, the subgrade modulus that we got, it is 30 meganewton per meter cube. So let us write that down. So subgrade modulus using the square plate. So if B1 is equal to 305 millimeter, that means corresponding to B1, that means corresponding to the square plate, we are getting subgrade modulus is equal to 30 meganewton per meter cube. So K1, K1 is 30 meganewton per meter cube. Okay. So next, what is written over here? Determine the subgrade modulus value for a footing with dimensions 2 meter by 4 meter. So what is the footing dimension? B footing is equal to 2 meter. Length of footing is equal to 4 meter. Okay. So, and here it is mentioned that the depth of the foundation and depth of the plates are the same. Okay. So that means there is no need to incorporate the depth correction. There are mainly three corrections. One is shape, another one is size, and another one is depth. Okay. So three corrections are there. if the depth of the plate and the foundations are same. That means if we conduct a plate load test at the same depth to that of the foundation, then there is no need to consider depth correction. Okay. So here it is mentioned that the depth of the foundation and the depth of the plate are same. So there is no need to find out the depth correction. What we need to do is that since Tarzagi did all the tests using a square plate, and here the footing is rectangular, so that means we need to incorporate the shape effect. And also the size of the footing is 2 meter by 4 meter. That means it is different to that of the size of the square plate. Obviously it will be different because this is a rectangle, that one is square. So that means we also need to incorporate the size effect. So in this particular question we'll incorporate size effect as well as shape effect. So here it is. So what is the value of k? K for first, this one is, understand this very clearly. Size effect. So this k will be for bf by bf actually. That means for a footing having dimensions 2 meter by 2 meter. See on this. Okay, square footing. We are extrapolating the value of subgrade modulus of a square plate from a square plate to a square footing having size bf by bf. So let us find it out. So what is k1? K1 is 30. What is the value of b in this case? B is same as that of bf. B is same as that of bf, that is 2 meter. What is the value of b1? It is 0.305 meter. So what is the value of 2b? 2b means 2 into 2 square. So if we calculate this, it will come 9.96 mega Newton per meter cube. Okay, so now we have find out. So now we just find out. We have found out the subgrade modulus for a footing having dimensions 2 meter by 2 meter. But in the question it is mentioned. That the footing is 2 meter by 4 meter. So we got the subgrade modulus for a square footing having dimensions 2 meter by 2 meter. Now we need to uh, you know now we need to find out the subgrade modulus for a rectangular footing having dimensions 2 meter by 4 meter. So this one is size effect. Okay, now shape effect. We are now finding out the subgrade modulus for a rectangular footing from the square footing. Okay, so shape effect. Now for stiff clay or clay soil, for stiff clay or medium dense sand, the shape effect, we can incorporate the shape effect using this equation. This equation. So what is L in this case? L is the length of the foundation, B is the breadth of the foundation. Okay, so and this K1. What is K1 over here? This K1 is equal to the subgrade modulus that we found out from the first one. Okay, the first equation, that is the subgrade modulus of the square footing. Okay, the square footing, that is after the size effect. After the first one, the size effect, the subgrade modulus that we found out. Okay, that one. So this corresponds, this one, this K1 is the subgrade modulus corresponds to a larger square footing, that is BF by BF. Okay. So what was the subgrade modulus value of the larger square footing? This one, 9.96 meganewton per meter cube. So K1 is 9.96 meganewton per meter cube. Okay. So what is L in this case? L is 4 meter and BF is 2 meter. Okay. So now if we incorporate all these values in this equation, we get K1 is 9.96. What is L? L is 4 meter, B is 2 meter plus 0.5 divided by 1.5. L is 4 meter, B is 2 meter. Okay. Now if you calculate all these, okay, if you calculate this equation, you will get K value. If you calculate, you will get K is equal to 8.3 meganewton per meter cube. This is the subgrade modulus for the rectangular footing having dimensions 2 meter by 4 meter. Okay. So this is the answer. So if you guys have any problem, if you have any doubt in this question, please let me know. If you have any problem, please let me know, or else I will proceed to the next problem. I am giving you a couple of minutes to go through this problem once. If you have any problem in these slides, you may tell me now. Shall I move to the next question? Shall I proceed to the next question?
Yes, sir.
Okay. So what is the second question? A plate load test done on medium dense sand. Similar type of question, but all these questions are different. There are slight differences between all these questions. Okay. So see, a plate load test done on medium dense sand using a square plate the same size, 305 millimeter, gives a subgrade modulus of 30 meganewton per meter cube. Determine the subgrade modulus value for a footing with dimensions 2 meter by 4 meter. Okay. But now here it is mentioned, you see the depth of the foundation is 1.5 meter below the ground surface, but the plate load test was conducted at the ground surface. Okay. In the last question that is solved, in that question you see the depth of the footing was the depth of the foundation and the depth of the plates were same. But in this particular problem, the depth of the foundation is 1.5 meter below the ground surface. Okay. So in this particular problem, the depth of the foundation is 1.5 meter below the ground surface, but the plate load test was conducted at the ground surface. Okay. So now let's see. What we need to do is that we need to incorporate the depth effect over here. Okay. So first of all, what we need to do is that what is the size of the square plate? It is the size of the plate is that is okay. B1 is 305 millimeter, and the subgrade modulus, that is K1, it is 30 meganewton per meter cube. So here we have been asked to find the subgrade modulus for a footing with dimensions having 2 meter by 4 meter. That is, breadth of the footing is equal to 2 meter, length of the footing is equal to 2 meter. Okay, so now the depth of the foundation. So depth of the foundation is 1.5 meter below the ground surface, but the plate flow test was conducted at the surface. So depth of the plate, okay, depth of the plate is 0 over here. So for this problem only, we need to incorporate the depth effect along with the size and shape effect. Okay. So first of all, we will incorporate the size effect for this problem, because the plate load test was done using 305 millimeter, like we did in the previous case. And this particular when we have been asked to find out the subgrade modulus for a footing having dimensions 2 meter by 4 meter. So first of all, like in the previous case, we will find out the subgrade modulus for 2 meter by 2 meter footing. Okay, so I'll just write it down. So k dash is equal to k1 b1 plus b by 2b. So this one is the equation. So this one is the equation. So what is b1? B1 is 305 millimeter. And what is k1? K1 is 30 meganewton per meter cube. So k1 is 30, b1 is 0.305 plus, what is the breadth of the foundation? Breadth of the foundation is 2 meter. This one is bf. B is same as bf, that is 2 meter, and this one is also bf. So 2 into 2 meter square, this one comes to be 9.96 meganewton per meter cube, like we did in the previous case, the same thing. Okay, so now along with this, so this is the subgrade modulus for the footing having square for the square footing having size 2 meter by 2 meter. Okay, so now after this we'll incorporate the shape effect, that is, we will find out the subgrade modulus for the rectangular footing 2 meter by 4 meter. Okay, so now let's come to that. Like we did in the previous case, this is also similar. So k is equal to k dash, this one will come over here. So let me write down the formula once. L by b plus 0.5 divided by 1.5 L by b. So this one is the equation. Okay, so now let's write down all these things. So k dash over here, it is 9.96. What is L? L is the length of the foundation. Length of the foundation is 4 meter. The breadth is 2 meter plus 0.5 divided by 1.5 L by b. So what is L? L is 4 meter. Breadth is 2 meter. Now if we calculate this like we did in the previous case, we will get this k value is equal to 8.3 meganewton per meter cube. Okay, so till now it is almost similar. It is similar to the last problem, but in the question it is mentioned. In the question it is mentioned the depth of the foundation is 1.5 meter below the ground surface, while the plate load test was conducted at the ground surface. So that means we need to incorporate the depth effect. Okay, because the depths of the plate and the foundations are not similar. Okay, so now the depth effect. So depth effect. So what is the formula for depth effect? It's K is equal to K1 1 plus 2 d by b. Now one thing we must keep in mind before using this depth effect, that this is only, the depth effect, the complete depth effect is, we must incorporate this depth effect only when there is cohesionless soil, that means sand or gravel, all those things. Cohesionless soil, okay, we must incorporate the depth effect when there is cohesionless soil, because in cohesive soil, the K value, that is the subgrade modulus, doesn't depend upon the depth. Okay, doesn't depend upon depth. Cohesionless soil, on the subgrade modulus in case of cohesionless soil only depends upon depth. Okay, not the cohesive soil. So we'll incorporate this only when there is cohesionless soil. So in this question, it is mentioned. You see that the test was done on a medium dense sand. So we must incorporate the depth effect. And one thing we must keep in mind, that this factor, only this 1 plus 2 d by b, should not be greater than 2. Okay. So let's solve this. Df is the depth of the foundation. B is breadth of the foundation. So first let us calculate what is 1 plus 2 df by bf. So first let us calculate what is 1 plus 2 df by bf. Okay. So 1 plus 2 into, what is the value of df? The df is 1.5 meter. The depth of the foundation is 1.5 meter below the ground surface. So df is 1.5 and the breadth is 2 meter. Okay. So now if you calculate this term, you will get this term, it will be 2.5, and now 2.5 is greater than 2. Okay, so if this value, this 1 plus 2 df by bf, if this equation becomes greater than 2, then we must consider 2. Okay, because this cannot exceed 2, this should not exceed 2. So if so now this value comes out to be 2.5, so we must consider this to be 2. So this one will be 2, that means the k value will be k1 into 2. So what is k1? The K1 is the subgrade modulus of the rectangular footing that you got after incorporating the shape effect. Okay. So this one is shape effect. You incorporated that into the size effect. That is after finding out the subgrade modulus for the square footing, you incorporated the shape effect to find out the subgrade modulus for the rectangular footing. So this one, okay, 8.3. So this one is 8.3 into 2. So 8.3 into 2 will be 16.6 meganewton per meter cube. Okay. So after incorporating the shape effect, size effect, and depth effect, the subgrade modulus comes out to be 16.6. Okay.
Sir,
Okay.
sorry to interrupt.
Okay. Tell me if you have any problem. Please tell.
Sir, K1 is, it should not be 30,
Hmm?
which you have considered earlier example. K1.
Yes.
K1, is it not 30?
Look, each time
Or
each time the value of k1 will change. You see, what was the original k1, you can denote it by anything. Okay, the if you see, the k1 was 30 for the
hmm,
square plate of 305 millimeter by 305 millimeter. Okay. uh, 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 Understand this very clearly. Okay, see, this one is a very
okay.
important thing. The k1 value that we considered in the first place, in this case you see the k1 K1 was found out using a plate having size 305 millimeter by 305 millimeter. Okay.
Hmm.
So what we did is that after this plate load test, we extrapolated this plate, the value of subgrade modulus to a square footing having a size 2 meter by 2 meter. Okay. In that case, see,
It
in
came out
you
9.96.
see k dash was 9.96. Okay.
Hmm.
So now in this question, you see, after now in depth effect, let me write it like k triple dash. Okay, it will be easier, right? This one will,
Yes.
yes. So no, not triple dash. Actually, this one is triple dash. This one will be like
K. Very
no, k dash. This one. Uh,
good.
oh, let me give it k double dash, and this one k triple dash. Okay, I think this one is easier. So see, so first one, this one. So k dash is equal to 9.96. So 9.96 comes over here. This one is k double dash, and the depth effect will be k triple dash, and this one will be k double dash. So k double dash is here. You see, it is 8.3. So it is 8.3, right? K double dash. So now, have you understood?
Yes, sir. Yes, sir.
Okay, okay. So so from now I'll be using all these things. Okay, k1, k single dash, double dash, and triple dash. Okay, okay,
Fine.
okay. So any more doubts in this question?
No, that's it.
Okay. So now let's come to the third question. So what is the third question? See, a plate load test done on medium dense sand using a square plate, same as that of the last two questions, gives the subgrade modulus of 30 meganewton per meter cube. Determine the subgrade modulus value for a footing having dimensions 2 meter by 3 meter. Okay. The depth of the foundation is 1 meter below the ground surface. Fine. But here comes the but. But the plate load test was conducted at a depth of 0.5 meter below the ground surface. Okay, that means the depth of the footing is 1 meter below the ground surface, and also the plate load test. The plate load test was conducted at a depth of 0 0.5 meter. The plate load test was not conducted on the surface in this case. Okay. So for this problem also, we need to actually incorporate the depth effect. Okay. For this problem, we need to incorporate the depth effect in such a way that it incorporates the influence of depth. See, the depth of the plate here is 0.5 meter. In the last case, the depth of the plate was not zero point 0.5 meter. It was on the surface. But in this question, the depth of the plate is 0.5 meter. So how we will solve this question? So in this case, we will do like what we did in the previous case. We will find out the subgrade modulus for a square footing. That is, we'll incorporate the size effect. After incorporating the size effect, we will incorporate the shape effect for the rectangular footing. Here it is a rectangular footing having dimensions 2 meter by 3 meter. After that, we will incorporate the depth effect. But here the plate was 0.5 meter below the ground surface. Okay. So let's get started. So the B1, that is the depth that is the dimension of the plate, is 305 millimeter. Fine. subgrade modulus, that is K1, subgrade modulus corresponding to the plate having dimensions 305 millimeter by 305 millimeter. So now size effect. This one is medium dense sand. So similar thing that we did. Size effect. In the last two questions, the footing size was, I think, 2 meter by 4 meter. In this question, it is 2 meter by 3 meter. Okay, so let us incorporate the size effect. That means we will find out the subgrade modulus for the footing size 2 meter by 2 meter initially. So K dash. Yes. So K dash is equal to K1 B1 plus B by 2B whole square. The size of the footing is 2 meter by 3 meter. BF is equal to 2 meter. The length of the footing is 3 meter. So this one corresponds to 2 meter by 2 meter. So now let's write down all these things. So K1 is equal to 30 meganewton per meter cube. What is B1? B1 is 0.305 meter. What is breadth of the foundation? It is 2 meter. Now 2 meter by 2 meter square. If we calculate this, it will be 9.96 meganewton per meter cube. Okay. Now let's incorporate the shape effect, that is for the rectangular footing. Let me write it down over here. Shape. For the shape effect, what was the equation? It is k double dash. So here we find out, we have found out k dash. Now we are finding k double dash. So what is k double dash? K double dash is equal to k dash L by B plus 0.5 divided by 1.5 L by B. Okay. So now what is k dash? K dash is equal to 9.96 meganewton per meter cube. What is the length of the foundation? It is 3 meter. 3 meter. What is the breadth? It is 2 meter plus 0.5 divided by 1.5. Length is 3 meter. Depth is 2 meter. Now, if you calculate this thing, it will come out to be 8.85 meganewton per meter cube. Okay, so that means now we have found out the subgrade modulus for the footing having size 2 meter by 3 meter, but we still haven't considered the depth effect. Okay, so that means it will give the same depth effect as if the rectangular foundation is placed at a depth of 0.5 meter, that is same that of the plate. Okay, so but it is not the case. The plate was at 1 meter below the ground surface, so we must incorporate that effect. So how to incorporate that effect? We have found out k double dash. Now we need to find out k triple dash. That is to incorporate the depth effect. So how we will do that? We need to find out here the difference of depth. That is del d. Okay, del d. What is the difference of depth between the foundation and the plate? Df and the plate. The foundation was at a depth of, the depth of the foundation is at 1 meter, and the depth of the plate was at 0.5 meter. So the difference in depth is 0.5 meter. Okay, so now we need to incorporate this effect. How we will incorporate this effect? See the last equation. This this equation. See, 1 plus 2 df by bf. We will use this equation, but in this way. The depth factor was 1 plus 2 df by df by b. In this case, it will be 1 plus 2 del d by b, the difference between the depths of plate and the foundation. So it will come out to be 1 plus 2 into, what is the difference? 0.5 by b. What is the b? B is 2 meter, I believe. Yes, it is 2 meter, the breadth of the foundation. Now, if you calculate this, it will be 1.5. Okay. So now it is not greater than 2, so we will consider 1.5. So k triple dash will be k double dash into this factor. Okay. 1.5. So what is k double dash? So what is k double dash? K double dash is 8.85 meganewton per meter cube into 1.5. That will come out to be 13.28 meganewton per meter cube. So in this way, we are incorporating all the effects, the size, shape, and the depth, the difference in depth. Okay. So if you have any problem, you can ask me now. There is a question in the chat box. Let me see. So what is the, so in the chat box, please, what happens if the depth of the plate is deeper than the depth of the foundation? Okay, this one is a very good question. So in that case, you must take the mod of the difference. Okay. In that case, you will take this, the mod. Okay. You will just take the mod. Okay. So if the plate is at a greater depth than the footing, you must take the mod value, only the positive side. So if you still have any problem, you can ask me, or I will proceed to the next problem. You may take a couple of minutes to understand this problem. This one is a very interesting problem.
Hello, sir.
Yes, tell me please.
As you said that the depth effect is to be considered only if it is a sand, right?
Yes, because for cohesive soil, the subgrade modulus doesn't depend upon depth.
So means we need not to calculate that factor k triple.
Yes. If there is clay, suppose in this problem, if the soil is clay, in that case, there is no need to consider the depth factor. Okay, only size and shape factor.
Okay.
Okay. So any
So
other?
size and shape factor are they are to be calculated for both, whether it is a sand or clay, right?
Yes, and one more thing, the size effect for the clay is different. The equation is different. I will show it. There is another problem. In that problem, I will use clay. Okay. In that problem, I will show what to do. Okay.
Okay.
Okay. So shall I proceed to the next problem?
Yes, sir.
Let me see if there is any question in the chat box. Okay, fine. So now let's come to the fourth question. So here in this question, the plate load test done on stiff clay. See, here it is stiff clay. Using a square plate of size 305 millimeter gives a subgrade modulus of 50 meganewton per meter cube. Determine the subgrade modulus value for a footing having dimensions 2 meter by 3 meter. The depth of the foundation and the depth of the plates are same. Okay. So here it is stiff clay. In the last problems, in the last three problems, the soil was cohesionless soil, medium dense sand. But here it is stiff clay. So now, as I've told just now, we need to incorporate the shape effect, but the formula for the equation for the size effect actually to incorporate the size effect is different from to that of the cohesionless soil. In the cohesionless soil, for the cohesionless soil, we used to use. Let me write it down. Size effect for cohesionless soil, it is K dash is equal to K1 B plus B1 by 2B. Okay, we have used this for the for the last three questions. For the cohesive soil, the size effect is K dash is equal to K1 B1 by B. This, okay, to incorporate the size effect. That is, if we want to find out you know square footing, the subgrade modulus for a square footing, we need to use this size effect. Okay, for BF by BF footing, we need to use this equation for cohesive soil. And the shape effect, the shape effect is same for both the soil. For cohesionless and cohesive soil, the shape effect is same. So let me solve this problem. You will understand what I'm doing. So let me write down all the information. So the size of the square plate B1 is 305 millimeter. The subgrade modulus is equal to 50 meganewton per meter cube. The footing, okay, the size of the footing BF is equal to 2 meter. The length of the footing is 4 meter. No, not 4 meter, it's 3 meter. One minute please. This one is anyway, let me just cut it like this, 3 meter. So now let's solve this problem. So first let us incorporate the size effect. Give me a minute please. Okay, so I can see there is a question in the chat box. So the question is formula for shape effect, the same for square, rectangular, and circular foundations. So here we are discussing only for rectangular and square foundations. Okay, the shape. Generally, we don't use circular plates uh, for plate load test. Okay, we don't use. But if there is a circular footing, then it's different. There is some equations, but it is not in the scope of this course. Let's give me a minute. So we were solving the fourth question, right? So we are solving the fourth question, right? Okay, so sorry, there was some malfunction over here. There is some malfunction. I will sort it out soon. Okay. So now the fourth question. So what I was saying, can you see the slides now? Hello, can you guys see the slides? Are you able to see the slides? Okay, fine. So now, as I was saying, this is the shape factor. This is the size effect, the size factor to incorporate the size effect for the cohesive soil, and this one is for the cohesionless soil. So in this question, let us write us down all the parameters that are given in this question. So B1 is equal to 305 millimeter, that is the size of the plate, and the subgrade modulus, that is the K1 corresponding to B1, is 50 meganewton per meter cube. K1 is 50 meganewton per meter cube. Fine. What are the other things? The size of the footing is 2 meter by 3 meter. 2 meter, and length of the footing is 3 meter, right? So now first of all, let us incorporate the size effect. So first of all, we need to find out K dash. So K dash is equal to K1 B1 by B. This one here it is cohesive soil. So K dash equal to K1 B into B1 by B. So what is K1? K1 is 50 over here. What is B1? That is the dimension of the plate. It is 0.305 meter. And what is the breadth of the foundation? It is 2 meter. Okay, so the answer will come out to be, if you calculate this, it will be 7.63 meganewton per meter cube. Okay, 7.63 meganewton per meter cube. So this K dash corresponds to a plate having dimensions BF by BF. That means 2 meter by 2 meter. Now we'll incorporate the shape effect. This is a square footing. Now we'll incorporate the shape effect. So now K double dash. K double dash is equal to K dash into L by B plus 0.5 divided by 1.5 L by B. See, the shape effect is similar. Okay, the shape effect is similar uh, in case of clay soil as well as cohesionless soil. So now let us write down all the values of all the parameters over here. So K dash is equal to 7.63 meganewton per meter cube. What is L? That is the length of the foundation. It's 3 meter. It's 3 meter. What is the breadth of the foundation? It is 2 meter plus 0.5 divided by 1.5 into 3 by 2. Now if you calculate this, it will come out to be 6.78. 6.78 meganewton per meter cube. So we have incorporated both the size effect and shape effect. Okay, this one corresponds to the footing having dimensions 2 meter by 3 meter. Okay, and since in this case the soil is cohesive soil, stiff clay, that is cohesive soil. So in this case In case of cohesive soil, the subgrade modulus doesn't depend upon depth, so there is no need to consider the depth factor. Okay, if the depth of foundation and depth of the plates that are same in this problem, if the depths were different, still there was no need to consider the depth factor. Okay, so this one is the answer. And only we need to incorporate the size and shape effect. That's all. So have you understood this problem? If you have any doubts, you can ask me now. Or else I shall proceed to the or else I will proceed to the next problem. If you have any problem in this question, please let me know. Shall I proceed to the next problem? Okay. So the question number 5. So what is question number 5? Estimate the immediate settlement. Estimate the immediate settlement of a concrete footing having dimensions 1 meter by 1 meter in size, founded at a depth of 1 meter in silty soil, whose modulus of elasticity is this 90 kg per centimeter square. The footing is expected to transmit a unit pressure of 200 kilonewton per meter square. Okay, so here we have been asked to find out the immediate settlement. Okay, in this question we have been asked to find out the immediate settlement. Okay, so what is immediate settlement? Let me first tell you. uh, Immediate settlement is what you observe after applying the load on the foundation immediately, say within 7 days. Okay, in cohesionless soil, the immediate settlement will occur very fast because the permeability of cohesionless soil is very high. So permeability is very high and it is very much compressible. So it will get compressed very easily after applying the load in case of cohesionless soil. Okay. Uh, so the formula of immediate settlement for both the soils, that is cohesive and cohesionless soil, are same. In case of cohesionless soil, immediate settlement is maximum. There is no need to consider the primary settlement. That will occur due to consolidation. Okay, primary consolidation. This one is immediate consolidation. But in case of cohesive soil, after some days, let's say 7 days, beyond 7 days, we will observe consolidation for few more days, for some days. So that is primary consolidation, where the excess pore water pressure will get dissipated. Okay, we will come to that problem. First, let me solve this one. So what is the formula for the immediate settlement? So what is the formula for immediate settlement? Let me denote it by SE, that is elastic settlement. So it is QB 1 minus mu square by ES into IF. Now let me just tell you what are these parameters. This Q is net pressure acting on the foundation. Okay, net foundation pressure. This B is the breadth of the foundation. Mu, what is mu? Mu is the Poisson's ratio for the soil. Poisson's ratio of soil. What is ES? ES is Young's modulus of soil. That is modulus of elasticity. Modulus of elasticity. Okay. What is IF? IF is influence factor. Okay. So as you know, the footing, shallow footing can be both flexible and rigid. Okay. So what happens in case of flexible footing? In case of flexible footing, the settlement is not similar in the in all the at all the points of the footing. Okay, it's different, but the rigid footing is expected to settle similar. The rigid footing is expected to settle uniformly. Okay, that means the settlement value will be same at all the points. Okay, so now what is influence factor? Suppose this immediate settlement, we found out with using this we find out that the immediate settlement, we have suppose we have been asked to find out the immediate settlement for a rigid footing. Okay, so in that case, using this settlement, using this formula, we first find out the settlement, immediate settlement for the flexible footing. After that, we incorporate this influence factor. We incorporate this in influence factor to incorporate the effect of the rigid footing. I will show you here. I will do this, you will understand as I do it. Okay, so let's come to the problem. So let me write down all the parameters. So C is equal to Q. So what is Q? Q is the net foundation pressure. So what is the net foundation pressure? It is 200 kilonewton per meter square. So Q is equal to 200 kilonewton per meter square. Next, B. What is the breadth of the foundation? It is 1 meter by 1 meter. So B is equal to 1 meter. Fine. Now this ES. What is ES? ES is the Young's modulus of soil, that is 90 kg per centimeter square. Wait a minute, please. So B is 1.5 meter. Okay. So now what is ES? ES is equal to 200 kilonewton per meter square. So ES 200. No, sorry. ES is equal to 90 kg per centimeter square. Sorry. 200 is the net foundation pressure. So ES is 90 kg per centimeter square. 90 kg per centimeter square. And if we convert this to kilonewton per meter square, it will be 9000 kilonewton per meter square. Fine. So what is mu? The Poisson's ratio for what is this soil? It is silty soil. Well, generally the Poisson's ratio for silty soil is 0.35. Okay, it is not given in the question, so I am assuming it. It is 0.35. So now if we input all these parameters into this equation, so let me write down the equation once again. Let me write it down up to this. Okay, after that I will incorporate the influence factor. I will show it how it is done. So Q. So what is Q? Q is 200. This one. So 200. The breadth is 1.5 meter. 1 minus mu square. What is mu? Mu 0.35, 0.35 square. What is ES? ES is 9000. Okay. So here we are considering a rigid footing. Okay. So Now observe one thing. We need to find out this influence factor. Okay. So first of all, we need to incorporate the influence factor for the flexible footing. If the foundation is flexible, then up to flexible footing we will consider. But if the foundation is rigid footing, then we will incorporate the influence factor for the flexible foundation at the center, and after that we will incorporate the influence factor for the rigid foundation, which is 0.8. I will show it. So now if you follow this, I am sharing a table. Please let me know if you can see this table. Hello, can you see this table?
Yes, yes.
Okay. So in the question, the what the the breadth of the foundation was 1.5 meter by 1.5 meter. So the foundation in the question is 1.5 meter by 1.5 meter. Okay. So in this table, if you see in this table for the square footing, okay, for the square footing, at the center, if you are asked to find out settlement at a corner or center or average settlement for the flexible foundation only, then you will consider the corresponding values. But in the after that, you will only consider these values. You will consider L by B rectangle. If the footing is rectangular, then you will consider these values by calculating L by B ratios. Okay. In this question, it is a square footing and it is a rigid footing. So if you are asked to find out the settlement, elastic settlement for a flexible footing, then you will only use this part only. Okay, you will only use this part. And but here in the question, it is a rigid footing. So in case of rigid footing, you will not use this directly. Okay, you will not use this directly. It is recommended to use the influence factor for the flexible foundation at the center first. It is a square footing, so I will use this one first, 1.12. Then we will again incorporate the influence factor for the rigid foundation, which is approximately 0.8. We will not follow this. Okay, I will show it to you. So note it down, the influence factor at the center for a square footing is 1.12. Note it down. So here first I will incorporate 1.12 for the flexible foundation, and after that we will incorporate the influence factor for the rigid footing, that is 0.8. The influence factor for the IF value, that is the influence factor for rigid footing, is approximately 0.8. We'll incorporate that over here. Okay, now if you calculate this equation, if you solve this equation, you will get AC, that is the elastic settlement. AC will be equal to 0.020966 meter, that is 20.97 meter. Okay, so this one is the value of elastic settlement, that is immediate settlement. So have you understood? If you have any doubt, you can ask me, or I will proceed to the next question.
Hello, sir.
Yes, tell me.
That flexible influence factor, can we take the same which is given, that is 0.82 instead of point 0.8?
You can take, but you see, for rectangular square, for actually what it is recommended, uh, for rectangular footing, for square footing, everything, for every type of footing, the you must take this factor 0.8. It is constant, okay,
Okay.
it is an approximated
Okay.
value. In that table, the values are different, but it is recommended
Mm-hmm.
to use this factor only for all types of footing, for circular, square, rectangular, okay. It is
Okay.
a
Point 0.8 is
point
fixed.
eight. It is an approximated value. You can use all those factors. It will not be wrong. But if you
Mm-hmm.
use this, it will this will give you approximate answer. Okay. So so if
Okay.
you have any,
Understood.
if you have any other doubts, you can tell me.
No, that's it.
Okay. So let us proceed to the next question. Let me see if there is any question in the chat box. Okay. So question number 6. A soft, normally consolidated clay layer. A soft, normally consolidated clay layer is 6 meter thick with natural water content of 30%. The clay has a saturated unit weight of 17.5 kilometer cube, a specific gravity of 2.67, and a liquid limit of 40%. The groundwater level, the groundwater level is at the surface of the clay. Determine the consolidated settlement of the foundation. If the foundation load will subject the center of the clay layer to a vertical stress increase of 8 kN per meter square. So first of all, let us understand this problem. What is happening? So suppose there is a foundation like this. Okay. A soft, normally consolidated clay layer is 6 meter thick with natural content of 30%. The clay has a saturated unit of 17.4. Okay, so like this. So suppose there is a foundation. The depth is not mentioned, but but I am assuming that it is on the surface. So this one is the foundation, and it is mentioned over here that the groundwater level is at the surface of the clay. Okay, this one is the groundwater level, and the clay layer is 6 meter thick. This one is 6 meter thick. Okay, the natural water content is 30%. WC is 0.3. Okay, 30% natural water content. The clay has a saturated unit rate of 7.4, 17.4. That is gamma sat. Gamma sat is equal to 17.4 kilonewton per meter cube. The specific gravity of soil is 2.67. Okay, and the liquid limit of soil is 40%. That is WL is equal to 0.4 or 40%. The groundwater level is at the surface of clay. Determine the consolidated settlement of the foundation. If the foundation load will subject the center of clay layer here, center of clay layer over here, that is at 3 meter, to a vertical stress increase of 8 kilonewton per meter square. That is del sigma. Vertical stress increase is what? 8 kilonewton per meter square. So this one is clay layer. Okay. So here the maximum settlement will be from primary consolidation settlement. Okay, from consolidation, primary consolidation. So we will find out that consolidation settlement, primary consolidation settlement. So what is the equation for that? So the primary consolidation settlement, the equation is CC, that is the compression index, initial void ratio, E0 is one initial void ratio, H is the thickness of the clay layer, log of to the base 10 overburden pressure, overburden pressure at the center of the clay layer, that is at 3 meter, plus the stress increase at the center of that layer, at the center of, you know, the clay layer, divided by the overburden pressure at the middle of the layer. So this one is the equation. So what is Cc? Cc is the compression index. Fine. So what is the formula for Cc? It is 0.009 WL minus 10. What is WL? It is the liquid limit. So what is the liquid limit in this question? Liquid limit is 40%. Okay, so 0.009, and this WL is in percentage. So 40 minus 10, it comes out to be 0.27. Okay, now what is E0? E0 is the initial void ratio. So we know Es is equal to omega g. Okay, since the soil is completely underwater, this will be fully saturated in submerged condition. So saturation is 100%. So S is equal to 1. So E is equal to omega g. What is the natural water content? Natural water content is, I think, around 0.3, that is 30%. So it is 0.3. So E is equal to E0 is equal to 0.3 into what is G, specific gravity of soil solid, GS, it is 2.67. So G is 2.67. Now if you calculate this, it will come out to be 0.081, 0.801. So this is the initial void ratio. Okay, and H is the height, the thickness of the clay layer, that is 6 meter. This one is H. Now what is sigma 0? Sigma 0 is the overburden pressure, effective overburden pressure at the center of the clay layer. Okay, so what is overburden pressure at the center of clay layer? That is over here at this level, that is at 3 meter. Fine. So what is the what will be this? What will be sigma 0 at 3 meter? This is in totally submerged condition. So it will be gamma submerged into 3. So gamma submerged into 3. So what is gamma submerged? Gamma sat minus gamma W into 3. So what is gamma sat? Gamma sat is 17.4 minus 9.81 into 3. If you calculate this, it will come out to be 22.77 kilonewton per meter square. Okay, so now we have the values of all the parameters that are needed to solve this equation. See, we have Cc, we have 1 plus E0, we have the value of H, we have sigma 0, we have del sigma. What is the del sigma? It is the increase in the vertical pressure at the center of the clay layer. It is 8 kilonewton per meter square. So here we have everything. So now let us just incorporate all the parameters, or input all the parameter, all the values of all the parameters into this equation. Let us incorporate. So consolidation settlement, the primary consolidation settlement, SC, will be equal to, let me write down the formula. Okay, let me just enter all the parameters. So SC is equal to CC by 1 plus E0. So CC, what is CC? CC is 0.27. So 0.27 by 1 plus E0. So what is E0? It is 0.801. So 0.801 into height. What is the height of the clay layer? This layer, it is 6 meter. 6 meter. Okay, into log. So log of sigma plus del sigma. So what is sigma? The overburden pressure at mid depth, it is 22.77. 22.77 plus increase in the vertical pressure, it is 8 kilonewton per meter square. That is 8 divided by the original overburden pressure at the mid depth, that is 22.77. Okay. Now if you calculate this equation, you will get primary consolidation settlement is equal to 0.087 meter, which is equal to 87 millimeter. This is the answer. So have you guys understood? If you have any problem, you can ask me now. Please let me know if you have any problem in this. If you have any problem in understanding of this problem, please let me know. Shall I proceed to the next problem? Okay. So let's come to the final problem of this session. So what is the question? Determine the depth at which a circular footing of 2-meter dia be founded to provide a factor of safety of 3 to it if it has to carry a safe load of 1600 kilonewton, and the foundation soil has cohesion value of 10 kilonewton per meter square, phi value of 30 degrees. The unit weight of the soil is 18 kilonewton per meter cube. Use Terzaghi's analysis. Okay, so here we can see the unit weight, the phi value is greater is 30 degrees. In case of such values, we are advised to find out the bearing capacity by considering both the general shear failure theorem and local punching shear theory, local shear failure theorem for Terzaghi analysis. Okay, if we know if the phi value is greater than 35 or 36 degrees, general shear failure occurs. We need to consider that. But if the phi value is lesser than 27-20 degrees centigrade, then we are advised to assume that it is local shear failure. So this here the phi is 30 degrees. Okay, so we are supposed to consider both in because this is a intermediate value. So we are supposed to consider both the local shear failure and general shear failure, and after calculating the bearing capacity using by considering both the failure patterns, we are advised to consider the minimum one. Okay, the minimum of the general shear failure and local shear failure. But here in this question, I will just assume that the soil is behaving like general shear failure. Okay, so I will consider that. I will just assume that the soil will undergo general shear failure. So let us solve this. So the depth of the foundation is unknown. This one is a circular footing. Okay, the diameter is 2 meter. Fine. The factor of safety is 3. Okay, the factor of safety is 3 and the safe load is 1600 kilonewton. The safe load is 1600 kilonewton. Okay, so safe load is equal to 1600 kilonewton. Fine. And what are the other things that are given? The cohesion of the soil is 10 kilonewton per meter square. and the phi value is 30 degrees, and the unit weight is 18 kilonewton per meter cube. So here we have been asked to analyze this problem using Terzaghi's bearing capacity theorem, and we are considering general shear failure pattern. Okay, so let us solve this problem. So we don't know the depth of the circular footing. Okay, so what is the net QNF, net bearing capacity? Okay, so what is the net bearing capacity of a circular footing in case of Terzaghi's theorem? It is 1.3. This is the shape factor CNC plus gamma d in q minus 1 plus 0.3 gamma b in gamma. Okay, so for phi is equal to 30 degrees, if you use the Terzaghi's bearing capacity chart, you will get for 30 degree value, for 30 degree phi value, nc is equal to 37.2, nq is equal to 22.5, and n gamma is equal to 19.7. Okay, so now QNF. Okay, let us just incorporate all these values of all the parameters into this equation. So let us just write it down. So 1.3 into c, what is the value of c? It is 10. So 1.3 into 10, and what is the value of nc? It is 37.2 plus gamma. What is the unit weight of the soil? It is 18. And what is the depth? We don't know the depth. Okay, so depth is not known. What is nq? Nq is 22.5 minus 1 plus 0.3. What is the value of unit weight? Value 18 kilometer cube. 18 into the breadth. Breadth is 2 meter. Dia. Here we will consider the diameter. So b is equal to diameter over here. It is 2 meter. And what is n gamma? N gamma 19.7. For you must note one thing: for circular footing, we considered the diameter in place of this, in place of breadth. Okay, so b is equal to diameter, in this case that is 2 meter. So now if you calculate this equation, you will get QNF, this complete equation, you will get QNF is equal to 696.36 plus 387 df. Okay, the df is unknown, so df. So now what is the safe bearing capacity? Qs. What is the safe bearing capacity? It is QNF by f, factor of safety, plus gamma d. Okay, so QNF. So what is QNF? QNF is 696.36 plus 387 df. What is the factor of safety? Factor of safety is 3. So factor of safety is 3. Now plus gamma into d. What is gamma? What is gamma? That is the unit weight of cell. It is 18. So 18 into d. That is df, the depth of the foundation. If you calculate this, you will get QS is equal to 232.12 plus 147 df. Okay. Now what is the load intensity that is acting on the footing? In the question it is given, if it has to carry, the foundation has to carry a safe load of 1600 kilonewton. Okay, so 1600 kilonewton. So load intensity, that is actual load intensity, that means the pressure. So it is, so 1600 kilonewton is acting on a circular footing. Okay, so what will be the pressure or stress? So qa is equal to 1600 by area of the circular footing. So 1600 divided by pi by 4 into d square. What is the diameter? The diameter is 2 meter. Okay, so pi by 4 into 2 square, pi by 4 into d square. Okay, so if you calculate this, you will get this to be as 509.3 kilonewton per meter square. Okay, so you know the actual load intensity, that it is, that the intensity is coming from the load to the foundation, that is the load intensity. Now you know the safe bearing capacity, this. Okay, now if you equate both the equation, both the value, both this equation and this value, if you just equate this and this, okay, you will get the value of df, that is the depth of the foundation. So let me just write it down. So qs is equal to 232.12, so 232.12 plus 147 df, this one equals to, is equal to this 509.3, because the foundation has to carry this load safely, safe load. So 509.3, this one is the allowable load. So 509.3, so this one is 509.3. Now if you solve this equation, the df will come out to be 1.89 meter. So that is approximately 1.9 meter. Okay, so this one is the answer. So the depth of the circular footing will be 1.9 meter. So if you have any problem in this question, please let me know. If you have any problem, please let me know if you have any problem in this particular question. See,
No, sir.
I am still explaining this once again. In this problem, we have been asked to carry a safe load of 1600 kilonewton. See, we are just finding out the safe bearing capacity of the footing using this formula. We are just finding out the shape, the the safe bearing capacity, that is qs, and we are equating both this one, the load intensity that is coming from the safe load of 500, that is 509.3 kilonewton per meter square. This is the pressure that is coming from the safe load of 1600 kilonewton, and we are, and we here we are equating the equation with that value. If we solve this, we are solving that, and here we are getting df is equal to 1.89 meter, that is 1.9 meter. So that's all. So that's all for today. I hope you have all understood what I have solved in this session. If you have any doubts, in any problem, you can just tell me now.
No, sir, no doubts.
Okay, so in that case, I am concluding today's session. We will meet next week. Okay, so okay, so bye for now. Goodbye. Have a nice evening. Good night.